where mysteries reside. And that bothered me. What does that mean? And I've been chewing on that for over a year now. Metaphors reign. See, when we don't really understand something, we give it a fancy name to hide the fact that we really don't understand it. That's part of what's going on here. I want to contrast science with technology. Most of us use those terms as equivalencies. What's the difference between science and technology? There's a very important difference. By the way, something else I just mentioned as I grow in the word, I'm convinced there are no synonyms. I think two words can be synonymous in that they mean almost the same thing. But watch out for that word almost. When Matthew uses the term kingdom of heaven, and Mark, Luke, and John use kingdom of God, 99 out of 100 commentators say, well, those are synonymous. No. Because this kingdom of heaven is a genitive of source, not a genitive of apposition. And Matthew's being more precise. And out of that comes a whole discovery. Because he uses that term 33 times. At 5 times he used kingdom of God, which proves that they're not synonymous. So the point is, watch out for the so-called synonyms. There are treasures there. Well, science and technology, we tend to use synonymously. No. Technology produces useful products. Technology produces useful products. That's why we have computers and pacemakers and thousands of appliances, information appliances, and other kinds of appliances in our lives, because they're useful. That's technology. Science has become a religion with its own priesthood. And we need to be on the guard of that, because it's a subject of presuppositions, myths, and so forth. Now, let's talk a little bit of the milestones of influence throughout, Johannes Kepler in the 16th century, he discovered that planets are in elliptical orbits with sun at one of the foci, that the sun's radius vector sweeps equal areas in equal times, and that the planets' squares of the periods are to each other as the cubes of their mean distances. Now that, in his day, was a profound advance in understanding that explained the motions of the planets in the solar system. And it was within a decade later that another guy was born by the name of Sir Isaac Newton. And he carried that principle of Kepler substantially. He established the basis of classical mechanics, advances in optics, differential and integral calculus. And he was a serious Christian, by the way. That's the other thing interesting about these early founders. You may not know that Sir Isaac Newton wrote over a million words on Daniel and Revelation. I have the copies. It's interesting reading. He wrote on hermeneutics. But he's most well known, and he changed the world with his what's known as the inverse law of universal gravitation. And I want to talk about this because this one contribution of his changed the whole scientific landscape. And the inverse square law of the theory of universal gravitation. And what most astronomers fail to do is recognize that inverse square law aspect of that. This was his equation, that the gravitational force is equal to a constant having to do with units. It's the product of the masses divided by the square of the distance between them. And we'll talk a little bit more about G. It's not that important for us here. But I want you to remember this d squared underneath. In other words, you take the product of the two masses that are being attracted, and you divide by the square of the distance between them. That gives you Newton's law of gravitation. The whole field of astronomy is obsessed with gravity, but they fail to really understand that d squared thing, and I'll show you what I mean by that. Well, after Newton, we run into a guy by the name of Ben Franklin, 1706 to 1790. And while he did many things in his life, for our purposes tonight, there's one event had. The amazing thing was he wasn't electrocuted. He was stupid enough to fly a kite during a lightning storm. And he risked electrocution, but he determined that the sky was inherently electrical in nature. And the entire scientific community chose to ignore that. It's amazing that it took, several centuries for that to be realized in the scientific community. It's still just being recognized by the astronomers. I'll show you what I mean as we go. After Ben Franklin, we have a guy by the name of Michael Faraday, 1791 to 1867. He's the one that pioneered the concept of electromagnetic fields. In fact, Albert Einstein kept a photograph of Faraday on his study wall alongside Isaac Newton and James Clerk Maxwell. Faraday was highly religious. Here's another Christian, member of the Christian sect that demanded total faith and commitment. And even the biographer said he had a strong sense of unity of God and nature pervaded in his life and work. Boy, I hope they say that about all of us in our epitaph, if you will. Now we come to a guy that we're going to talk a little bit about tonight, because he's ignored by most people who get into, unless you either ignore him or you really get into him. Very few people in the middle. A guy by the name of James Clerk Maxwell. He codified the basis of all that we know about electrical science and engineering into a self-consistent set of equations. Originally 20, finally boiled down to 4, but all about electric currents, magnetic fields, that they intrinsically are connected. That magnetic fields, electric currents, magnetic fields are intrinsically involve a common behavior. And that electromagnetic energy propagates through space. So far, so good. Ranked with Sir Isaac Newton and Albert Einstein in the fundamental nature of his contributions in quantum theory, electromagnetics and electrostatics, thermodynamics, information theory, and cybernetics. Quite a guy, by the way. Okay? But along comes a guy by the name of William Thomson, who gets knighted, and he's known as Lord Kelvin. And from 1824 to the turn of the century, to 1907, he becomes an incredibly influential scientist in 1900 Great Britain. Lord Kelvin, profound influence. He was knighted for his work in thermodynamics. That's the good news. Let me give you the bad news. He was an outspoken critic and very pessimistic about the future of electricity and electromagnetic theory. He predicted that radio and wireless telegraphy had no future. Now, we laugh at that today, but he cast a pallor on that as far as the British scientific community is concerned. And as you study the history of science, you'll discover that from Kelvin on, the British Astronomical Society goes one way, and a whole nother field of study is ignored by them that comes out of Norway, Sweden, and the northern latitudes. And that's what we're going to focus on tonight. But Kelvin was a cloud on this whole picture. And so I want you just to recognize the negative influence of this one man. Now, before we go any further, you need to have something else that I want you to do. I want us tonight, we want to have a way to somehow relate to extreme magnitudes. Scientists use fancy numbers to represent large magnitudes, but often they don't really understand that. I remember I was with Edward Teller and his sidekick Norris Keeler, and they were talking about 10 to the 17th something or other, and I said, gee, that's more than there are seconds in the history of the universe. They looked at me startled. What do you mean? Well, you're the guys who are going to try and tell me that the universe is about 15 billion years old. That's only 10 to the 17th seconds. They were startled. Just do the math. See, they use those numbers, but they didn't really have an appreciation of the science. We need to have an apprehension. Let me give you a new word that's in our vocabulary today to demonstrate what I'm talking about. We have a new word called trillion. How much is a trillion? I have yet to find a congressman or senator that can answer that question. Now, I'm serious. How much is a trillion? Okay. My old friend Bill Ruggles is here, and he and I got into some strange investments years ago. And if I said to Bill, I know I owe you some money, but I'm going to pay you back in 1,000,000 seconds. Bill would take out his calculator and a million seconds. Well, that's 12 days. I can live with that. Oh, I'm sorry, Bill. I misspoke. I'm going to pay you. I'm not going to 1,000,000 seconds. That's 12 days. I misspoke. I meant to say I'm going to pay you in 1 billion seconds. He gets his calculator out. How long is 1 billion seconds? 32 years. You see, that's not only a quantitative difference. That's a qualitative difference. He knows that ain't going to work. I said, oh, Bill, I'm sorry. I misspoke. I'm going to pay you back in 1 trillion seconds. How much is that? 32,000 years. You see the point I'm trying to make? Million, billion, trillion. 12 days to 32 years to 32,000. Those are qualitatively different. We live in an economy with 14 trillion gross domestic product per year, carrying a debt of 800 trillion. Come on, what are you talking about? Check it out, it's important. Well, now let's get back to our subject at hand. How big is our galaxy? We can talk about all kinds of things and still not relate to how big the galaxy is, okay? There is a model suggested in the handbook of the Celestial Handbook by Burnham, that's worth our consideration. It turns out it takes advantage of a coincidence. It turns out that the number of inches in a mile turns out to be about 63,300, give or take, the number of inches in a mile. It also turns out that in astronomy, a standard unit of measure is called an astronomical unit. It's the distance between the Earth and the sun, okay? It turns out the number of astronomical units, which happen to be about 93 million miles, the number of astronomical units in a light year is the same number, almost. They're almost the same number. The number of inches in a mile and the number of astronomical units in a light year. That's going to be useful to us just to build a model, okay? The distance from the sun to the Earth is called an astronomical unit. It happens to be 93 million miles. That's just a basic unit in astronomy. In Burnham's model, we're going to let 1 inch represent the distance from the sun to the Earth, and we're going to let 1 mile represent a light year. You with me so far? Okay. Robert Burnham's handbook, the Celestial Handbook's 3-volume standard stuff. Okay. Well, the sun is 880,000 miles in diameter. In other words, on our model, it's about 0.009 inches. So our sun, in our model we're going to build, represent a dot of a very sharp pencil. Call it like a period at the end of a sentence. That's going to be our sun. You with me? Okay. So it's 1/100th of an inch, a tiny little speck. All the planets will turn out to be within a 7-foot circle diameter. The Mercury would be 4/10 of an inch away from that dot. Venus would be 7/10 an inch from that dot. The Earth, by definition, would be 1 inch. 1 inch being an astronomical unit. You with me so far? Okay. Mars would be about 1.6 inches. Jupiter about 5 inches. Saturn about 9.5 inches. Uranus about 19.2 inches.